So this is from the Google Doc, the end of it on Thursday, the 11th. And this is connecting work that we calculate with the spring and finding the spring constant with the kinetic energy. So here's the first setup. You have a block that's of mass 0.3 kilograms, and a hand has pushed to compress it 15 centimeters, and the force is just holding it still. So the first question is, what is the spring constant? So right at this point where the block is at rest, then the force diagram looks like we have the force of the hand in this direction, and the spring obviously wants to push it over to the right. And those are balanced because it's at rest, it's not accelerating. So we could say then the spring force is 20 newtons, pushing to the right, and we've got spring force is equal to minus k times x, and so we've got 20 newtons is equal to minus k. The x distance that it's been compressed has been from this initial point over to the left, so it would be a minus 0.15 meters. Or if you're ever in doubt, your spring constant is always going to be a positive value. And so K is going to be 20 newtons divided by 0.15 meters, or 133 newtons per meter. And that's a perfectly good unit for the spring constant. So that tells you how stiff the spring is. Okay, so then the question is, sketch a plot of the spring force versus position during this compression. So if we say it goes from x equals 0 to minus 0.15, then the spring force starts at 0, and then it gets bigger, and it goes all the way up to 20 newtons. Okay, so something like that. Okay, you could have also drawn it like this. It's perfectly fine to draw it like that, force and x also. If you're just doing the absolute value, that's perfectly fine as well. But this is a force that's changing with position, the slope of this, the magnitude of the slope. If you take the absolute value of the slope, that still gives you this 133. So that's a way to find your spring constant, by looking at the slope of this force versus position. Next, it asked for this plot, determine the work done by the spring. So often we say work is force times displacement. In this case, we need to be careful because our force is not constant. And since it's not constant, we actually have to say work is equal to the integral of f dx, or it's the area under the curve, which is easier than doing the integral, but you can do the integral if you want. The area under the curve is just this area right here, the triangle, or it could have been over here, either way. So this work is going to be 1/2 base, which would be 0.15 times the height of 20, and that'll be Newton meters. So that will be 1.5 joules. Now we need to say, is it plus or minus? Okay, because area is always positive, but the work could be plus or minus. So let's figure that out. So as we look at this, the spring force is going that direction, but the displacement is going that direction. So that's an angle of 180 degrees, so that must be negative work. So altogether, the work done by the spring, in this case, is minus 1.5 joules. Finally, the net work is equal to the change in kinetic energy. So when we start the compression, it's at rest. When we finish it, it's at rest. So the change in kinetic energy, which is kinetic energy final minus kinetic energy initial, in this case is 0 because the hand starts from rest, pushes it, and that it ends up at rest. So there's no change in kinetic energy. So our total work is equal to 0, which means that the work done by the hand plus the work done by the spring must be equal to 0, or since this is negative 1.5 joules, the work done by the hand must be a positive 1.5 joules. So the hand did positive work, and this makes sense because the force of the hand is in this direction and the displacement is in that direction. That's the direction we went for X. They're both in the same direction, so that would be positive work. Okay, now we start with a different question. The hand is removed from the block. So here we have this coiled spring. The hand, which was there, holding everything still, is removed. Well, we know that this block is going to slide. It's going to pick up speed and head off to the right. And if there's no friction, once it leaves the block, so once it gets past this 15 centimeters, the question is how fast is it going? And so we can say, what is the net work done on the block? Because if we can find the work total, that's going to equal our change in kinetic energy. And in this case, our initial kinetic energy is equal to 0 because it started from rest. V equals 0 to start, and then this would be our V final. And so the work done is going to be, well, the only thing that's doing work is the spring, right? We've got the force of the spring. The hand's gone. The spring force is going to uncoil, and it's going to be in that direction. The X is going to be in that direction. So this time the work is going to be the same. It's just going to be positive. So the work done by the spring this time is going to be positive 1.5 joules because now we're going in the same direction. And that's going to equal our change in kinetic energy. So we have 1.5 joules is equal to kinetic energy final minus kinetic energy initial. That's 0. Kinetic energy final is then going to be, which is 1/2 mv final squared, is equal to 1.5 joules. So we can just, now we need to actually know the mass. So it was a 0.3. The mass was 0.3 kilograms. We have 1/2. V squared is equal to 1.5 joules. So V final squared is equal to, then the 2 will give us 3 joules over 0.3 kilograms. Our V final squared is equal to 10 meters per second squared. V final is equal to about 3.1 meters per second. Okay, somebody doesn't want to calculate work or kinetic energy and decides to do this. Okay, spring force equals 20. Yes, that's true. Once the hand is removed, the force is only in the X direction, so the spring force, okay, that seems fine. That seems okay. All right, so this is the acceleration. This is the acceleration at the beginning. The spring force is changing. Changes. It changes. It gets bigger the bigger the X is, which means when it's coming back in, the spring force gets smaller. So that means our acceleration in the X is changing. And this is where the problem comes in. The kinematics equations, at least this one, this, the assumption is, we derived it, the assumption is that acceleration is constant. So here's where the mistake is. We can't use that equation because our acceleration is changing. So it turns out that using this energy approach gets us a calculation that we could not get before, or we'd get the wrong answer. We'd get, if we use this approach, we get 4.5 meters per second instead of 3.1, which is wrong because the acceleration is not constant. It starts out at a high acceleration, but by the time it gets to the end, before it's leaving the spring force is 0, the acceleration is 0. It's just whatever speed it was going, which is, in fact, 3.1 meters per second. And so this gives us a hint into how it is that using work and energy lets us solve some problems actually in ways that are easier than we were doing before with force diagrams. But sometimes it allows us to work problems we couldn't even work otherwise.